In this video, I'm going to be going over some of the basic trigonometric identities, and we'll see these throughout the course. So the question here is, which of the trig functions are even and which are odd? Before I actually answer that question, I want to back up and talk about what we mean by this word identity. So a trig identity, or actually in math, an identity is any equation that is true for any value that you input into the equation. So an example is 1 times x is equal to x. This is an identity because no matter what value we select for x, the left side will always equal the right side. So I could put in square root 3, I could put in pi, I could put in the number e, I could put in 5,342 over 6. If I put any of those values in for x, or in fact any real number, the left side will equal the right side. So that is an example of what an identity is. In a trigonometry class, we have a lot of identities, and many of those identities deal with the trig functions where we pick any angle to be the variable. So now let's talk about the answer to this question. Which of the trig functions, so remember there are 6 trig functions, which of them are even and which of them are odd? Well, if you think back to an algebra course, a function is even if f of x is equal to f of negative x. So an example of this might be, well, let's say our function is x squared. So f of x is x squared. If I change the input to be negative x, well, negative x squared, that still comes out to x squared. So in this case, f of x is equal to, sorry, let me write it like that. F of x is equal to f of negative x. So that means this function is even. Okay, so this must be satisfied for a function to be even. A function is odd if negative f of x is equal to f of negative x. So suppose my function is f of x is equal to x cubed. So to verify that this is odd, we're going to say, well, what is negative f of x? That's negative of this whole function, and that just equals negative x cubed. And then f of negative x, well, that's going to be negative x cubed. A negative times itself still comes out to negative. So what we've shown is that negative of f of x is equal to f of negative x. That's true, so that means f of x is odd here. Okay, so we verified that this is true. All right, so of the 6 trig functions, some of them are even, some of them are odd. So cosine of theta is equal to cosine of negative theta. Cosine is an odd function. Cosine is an even function. And then the reciprocal of cosine is also an even function. So secant theta is equal to secant of, let me write negative theta. So those are the even functions. The odd functions are the other 4 functions. So sine of negative x is equal to negative sine of x. And again, I can use x, I can use theta. It doesn't matter. We just know that theta or x or whatever I input into a trig function represents an angle. Okay, so cosecant, which is the reciprocal of sine, that is also an odd function. And then the last 2 remaining trig functions. So tangent of negative x is equal to negative tangent of x. And then cotangent of negative x is equal to negative cotangent of x. So let's talk about why these are true. I'll highlight this with cosine first. So what this is saying is cosine of an angle is equal to cosine of negative of that angle. So let's just pick an angle on the unit circle. How about cosine of pi over 6? And we want to show that that is equal to cosine of negative pi over 6. So cosine of pi over 6, that is on the unit circle. It's right here. The coordinates there are root 3 over 2 and 1/2. So cosine of pi over 6 is equal to root 3 over 2. Now cosine of negative, so this angle right here was pi over 6. Negative pi over 6 is just going to be down here. And that has the same coordinates except the y coordinate is negative. So what we see is it has, whether I'm looking at pi over 6 or negative pi over 6, those both have the same x value. So this is root 3 over 2, and that is true. So I could do that for any angle on the unit circle or any angle in general. And those are going to be equal to each other. Okay. Now let's do something similar for sine. Okay. So let's pick an angle on the unit circle. How about, I don't know, 5 pi over 6. So sine of negative 5 pi over 6 is equal to negative sine of 5 pi over 6. Let's verify that. So 5 pi over 6, ooh, that's a bad x-axis here. Okay, so 5 pi over 6 is down here. And the coordinates there are negative root 3 over 2 comma 1/2. So that's for 5 pi over 6. And then negative 5 pi over 6 is just going to be in the opposite direction. So down here. And the coordinates there are the same coordinates as for 5 pi over 6, but we're going to have both coordinates negative. All right, so now let's look at this equation here. Sine of negative 5 pi over 6, well, I'm going to use the green coordinates here. So that's negative 1/2. It's just the y coordinate. And then sine of 5 pi over 6 is 1/2. So I get a negative of all of this is 1/2. So this is negative of 1/2. So these are both equal to negative 1/2. So I've verified that this equation is true. So you're not going to need to do that probably very often or ever. But what's important here is to know which of these functions are even and which of them are odd, and how these equations get set up. The next set of identities are called fundamental identities. And we've seen these a little bit already. But recall that on the unit circle, sine of theta we can treat as y over 1. And cosine of theta we can treat as x over 1. So sine always corresponds to the y coordinate. Cosine corresponds to the x coordinate. And then if I'm thinking about tangent in those terms, that's the same thing as y over x. Now, because sine of theta is equal to y, I can rewrite tangent as sine of theta and in place of y, and then cosine theta in place of x. So another way to think about tangent of theta is the ratio of sine over cosine. And then similarly, I'll go down here for cotangent. That we can think about as x over y, which is the same thing as cosine of theta over sine of theta. Okay, and then moving over to secant and cosecant. Well, cosecant is just the reciprocal of sine. So the reciprocal of y over 1 is 1 over y, which is the same as 1 over sine of theta. So the reciprocal of cosecant is just sine of theta. And then for secant, similarly, instead of writing this as 1 over x, I can write this as 1 over cosine of theta. So that's similar to 1 over x, and cosecant is similar to 1 over y. All right, so let's look at a couple examples of how we might use these identities. In a right triangle, let sine of theta be 5/13 and cosine be 12/13. Find the value of the 4 other trig functions. So this example doesn't say anything about the unit circle. So we just have a right triangle. Well, let's do a little bit better of a job here. We're going to have a right triangle. Okay. And doesn't matter where I put theta. I can't put it where the right angle is, but I can put it in either of the acute angle positions. So if sine of theta is 5/13, remember sine, we're dealing with a right triangle. We want to think of this in terms of hypotenuse, adjacent, and opposite. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So I know that that's 12 here. So I've got it pretty good. I have my triangle all filled out. So now I can get the other trig function values. We actually didn't need the triangle to find cosecant, as long as we know that that's the reciprocal of sine. So that's 13 over 5. Similar to secant, once I remember that secant is the reciprocal of cosine, I get secant without doing much work. Tangent of theta, though, I need all the values on that right triangle. So tangent is opposite over adjacent, so that's 5/12. And then cotangent is just the reciprocal of that, 12 over 5. All right. So we're just using some of our basic identities. Another way to do this for tangent and cotangent, let's do this. Tangent, as we set up here, is equal to sine of theta over cosine of theta. So I know sine of theta, it's 5/13. I know cosine of theta is 12/13. The 13ths cancel, and I get 5 over 12, which is the same thing as I got here. So that's another way you can do this. What we'll see in trig is that there's many ways of using these identities to get us, many different ways of using them to get what we want. All right, next example. Find the other 5 trig function values of theta, given that theta is an angle of a right triangle. Okay, so let's draw another right triangle. And we're going to say that theta is down here again. Actually, I'm going to do it up here just to show that it doesn't matter which of those two angles we use. And it says sine of theta is equal to 2/5. So sine of theta, 2/5. So sine is always opposite over hypotenuse. Okay, so now that I have sine, I can easily get cosecant of theta. That's just the reciprocal. But I need to do a little work to get cosine, secant, tangent of theta, and cotangent of theta. And the work that I have to do is I have to find this value y here. So I'm going to say 2 squared plus y squared equal to 5 squared. I get 4 plus y squared is equal to 25. Y squared is equal to 21. And then taking the square root, they'll say y is equal to square root 21. Excuse me. So I have that missing value on the right triangle. This is square root 21. So now that I have that, I can easily find these other 4 trig function values. So cosine of theta, cosine is the adjacent. So from this angle, the adjacent side is root 21 over the hypotenuse. So root 21 over 5. The reciprocal of that for secant is 5 over root 21. And then for tangent, that's opposite over adjacent, so 2 over square root 21. And then cotangent is just the reciprocal, root 21 over 2. Okay, and then the last identity in this this section is the Pythagorean identity. And the Pythagorean identity is an identity we'll use quite often. And as the name implies, has something to do with the Pythagorean theorem. So suppose I have this angle down here. If this, let's say I have this right triangle and the hypotenuse there is equal to 1. So the way that this relates, all these sides relate to each other, I can say y squared plus x squared is equal to 1 squared, or r squared. So y squared plus x squared is equal to 1. Now recall that on the unit circle, which this triangle would be in the unit circle because it has a radius of 1, the y coordinate corresponds to the sine value. So in place of y squared, I'm going to write sine of theta squared. In place of x squared, I'm going to write cosine of theta squared, and that is equal to 1 here. So the Pythagorean identity says, well, sine squared of theta, and how we write this, we usually write the squared in between the sine and the theta, like this, plus cosine squared of theta is equal to 1. So this is the Pythagorean identity. And again, this is quite useful. So anytime we have sine squared plus cosine squared, and I have the same angle, in this case, both theta, that will be equal to 1. And let me show just how this, just an example to verify this, or to kind of show how this works. Let's say my angle, and let's pick an angle on the unit circle. Let's go down to quadrant number 4 here, and let's say that angle is 7 pi over 4. The coordinates there are root 2 over 2 and negative root 2 over 2. So if I wanted to say sine of 7 pi over 4, and I'm going to square that, plus cosine squared of 7 pi over 4, that is going to be equal to 1. And so let's verify that. Sine of 7 pi over 4, that's the y coordinate, so negative root 2 over 2, but I'm going to square that, plus cosine of 7 pi over 4 is root 2 over 2 squared, and that's equal to 1. So negative root 2 over 2, that just means I'm going to square the tops and the bottoms. So negative root 2 times negative root 2 is positive root 4 over 4. Same thing, I get positive 4 over 4. Square root of 4 is 2, so this is 2 over 4, this is 2 over 4, so that's 1/2 plus 1/2, and that's just equal to 1. So that is an example of using the Pythagorean identity. And once again, an identity just means no matter what value I input in for the variable here, as long as I use the same value for every location of the variable, the left side will always equal the right side.